Hi everyone, welcome back. We're finally at the end of this long, dense, and meaty chapter, so let's get to it. This slide is from your textbook, and it is a great slide. It shows insulin and all the counter-regulatory hormones. First, it shows how the incretins will stimulate your pancreas to release insulin. So remember, insulin is the main anabolic hormone, and it helps control our blood glucose levels by signaling the liver and muscles and fat cells to take in glucose from the blood. Insulin is therefore used for energy, and if the body has sufficient energy, insulin signals the liver to take up glucose and store it there as glycogen. Now then we have all of our counter-regulatory hormones: glucagon, growth hormone epinephrine, and the glucocorticoids. So GHRH, which we haven't gotten to yet, in the hypothalamus, is going to stimulate the anterior pituitary to release growth hormone. And we'll also see that ACTH is another anterior pituitary hormone, and that will act upon our adrenal glands and stimulate that to release things such as epinephrine and our glucocorticoids. Okay? So glucagon is basically counter-regulatory to insulin. Whereas insulin was released from the beta cells of the pancreas, glucagon is released from the alpha cells. And glucagon stimulates glycogenolysis, or the breakdown of glycogen in the liver. This causes it to release glucose and raise our blood sugar level. Glucagon is, as I told you, an injection that diabetics will keep for emergencies in their refrigerator, and their family members should know that when their diabetic family member becomes unconscious and is hypoglycemic, they are to deliver the injection of glucagon to the patient, which will stimulate their liver to raise their blood sugar while you wait for EMS to show up. Okay? EMS should come and then give you some nice dextrose IVs. Growth hormone, epinephrine, and cortisol are also counter-regulatory hormones to insulin. And you can see here that growth hormone has the effect of decreasing carbohydrate utilization and stimulating and mobilizing catabolism of fats, both of which will also raise the blood glucose level. Epinephrine stimulates glycogenolysis from the liver and muscles, as well as stimulating the mobilization and catabolism of fats. The glucocorticoids, or cortisol, will stimulate protein mobilization and gluconeogenesis, the making of new glucose from alternate non-carbohydrate sources, such as from the amino acids, raising blood sugar as well. And you know this if you've ever taken prednisone. Sometimes you take it as a Medrol dose pack, and your doctor, pharmacist, or the pamphlet that's inserted with the medication will tell you that you're taking a glucocorticoid and it will raise your blood sugar. So expect this. Okay? All right, so that's a good slide just to kind of coalesce a bunch of information that you've learned. And I also realized that I forgot to just sort of label and put it out there for you, the terms hyperglycemia and hypoglycemia. So hyperglycemia simply refers to high levels of blood glucose, okay? Whereas hypoglycemia refers to low levels of blood glucose. And this is all, of course, relative to what is normal blood glucose levels. So your normal blood glucose when you're fasting, okay, after 8 hours, usually you have your blood drawn when you first get up in the morning, should be between 80 and 90 milligrams per deciliter. That's milligrams of blood sugar per deciliter of blood. And most labs will consider under 100 normal, but kind of targeting mostly 80 to 90. Postprandial, after eating, about 2 hours after eating, actually, so not immediately postprandial, your blood sugar should be less than 140. Okay, so a little bit higher after having food. So let's talk about lipids. Triglycerides are the main constituents of body fat in humans and other vertebrates, as well as vegetable fat. Triglycerides are triesters consisting of a glycerol backbone bound to 3 fatty acid molecules. In a moment, we'll discuss how to identify our triglycerides as being either saturated or unsaturated. You can see the triglyceride depicted right below the term there on the left-hand side. The middle picture is a phospholipid, and these are a component of all cell membranes. They form lipid bilayers because of their amphiphilic characteristic, which means that they have their hydrophobic fatty acid tail and their hydrophilic head consisting of a phosphate group. And then lastly, we have cholesterol. Cholesterol is an organic molecule. It's classified as a sterol. It is made by all animal cells, and it's only found in animal cells. And it's a structural component of all animal cell membranes. If you recall from Bio 155, you learned that it kind of gives both structure to the cell membrane and yet at the same time also gives it fluidity. So your body needs some cholesterol to make hormones, vitamin D, and some of the substances, the bile acids that help you digest your food. So it is a required molecule and it is not inherently evil, though some sources would like you to believe that it is. From a chemical standpoint, saturated fats are simply fat molecules that have no double bonds between carbon molecules because they are saturated with hydrogen molecules. Saturated fats are typically solid at room temperature. Here you have a picture of stearic acid in A that is a straight chain saturated fat. Unsaturated fats have crooked tails with double bonds. They are usually liquid at room temperature, or oils. Now let's look at the transport of lipids, which is a difficult subject. To understand how fat travels around our body is going to require some understanding of the distinction between what is a hydrophobic and hydrophilic molecule. You should know this already, but let's review it. A molecule is said to be hydrophobic or nonpolar if it repels water, while a molecule is said to be hydrophilic or polar if it attracts water. So in general, think about your blood vessels as waterways or the rivers of your body. If a molecule is hydrophilic, it can be transported in our bloodstream pretty effortlessly because it's not repelled by the water or the plasma or the blood. However, fat is hydrophobic. So to carry it around in water, it's going to need a transporter, kind of like a little boat, to carry it through that waterway, river, or blood vessel in our water, which is our blood. So what is a chylomicron? A chylomicron is an ultra-low density lipoprotein, and lipoproteins are particles that consist of triglycerides, phospholipids, cholesterol, and proteins, and they transport dietary lipids from the intestines to other locations in the body. The proteins that traffic collections of lipids are called apoproteins. Once bound to lipids, they are called apolipoproteins, and the protein vehicle that transport the lipids are called lipoproteins. And there's a lot of fuss about all these lipoproteins, but it's a crucial concept for you to understand that for the most part, Lipids are going to go nowhere in our body unless they are a passenger inside a protein-wrapped vehicle, which is called a lipoprotein. As their name suggests, lipoproteins are part lipid and part protein. They are mostly spherical structures which are held together by a phospholipid membrane, which contains free cholesterol. And I have a picture of a lipoprotein coming up. The lipoproteins that you're going to be familiar with are formed in the liver, and they consist of, as I said, lipids and protein, and you'll recognize them by their names: VLDL, LDL, and HDL. Let's get this straight. Our blood or our plasma is an aqueous solution, and we need to transport fats which do not want to be in an aqueous solution around our body. Cholesterol and triglycerides are hydrophobic. Okay, they're non-polar molecules. They're not soluble in plasma. And to be carried anywhere through our blood, they're going to be wrapped in a special protein transport vessel called a lipoprotein. On the next slide, when you look at the lipoprotein molecules, you'll notice that there are variable sized proteins on the surface of the lipid membrane that holds the structure together. The most important of these proteins are the apolipoproteins. The apolipoproteins on the lipoprotein molecules serve several purposes, such as they assist in the structural integrity and the solubility of the lipoprotein, and they serve as cofactors in enzymatic reactions. They will also act as ligands for situations when the lipoprotein needs to interact with the receptor of a cell. So let's look at these. Here's a chylomicron at the top and a lipoprotein at the bottom. And you can see the different parts of the lipoprotein molecules specified by icon. Now, your textbook doesn't go into this in depth, and this picture is not from your textbook. But I just want to make you aware that apolipoproteins will come in different shapes and sizes that will determine their class. And so you might have an apolipoprotein A or an apolipoprotein B. And apolipoprotein B is going to be really important for us when we get into studying heart disease. So apolipoprotein B is a apolipoprotein that's predominantly composed of proteins that are beta-pleated sheets, and they form lipoproteins that are lower in density. And you'll see they're highly associated with our LDL, our low-density lipoproteins. And these are the lipoproteins that give us problem for cardiovascular disease. So let's start looking at that. All right, cholesterol and heart disease is a big topic. It's really complex, and we're going to only scratch the very surface of it, okay? So these ApoB particles cause us lots of problems, and these ApoB particles, which 90 to 95% of them are LDL particles, are LDL lipoproteins in the plasma, are what will end up causing atherosclerosis. And what is atherosclerosis? It is the accumulation of these sterols and inflammatory cells, and actually the accumulation of the sterols inside of the inflammatory cells within an artery wall, which may or may not narrow the lumen of the artery. So let's get specific on that. Cholesterol is delivered to the arterial wall by penetration of the endothelium by an ApoB containing lipoprotein, which is actually transporting the cholesterol. So in other words, unless an ApoB containing lipoprotein particle violates the border created by an endothelium cell and the layer that it protects, the media layer, there is no way that atherogenesis is going to occur. You remember when we studied the blood vessels that you had that intima layer lining the inner lumen of our blood vessels, and underneath that was the muscular layer. Okay, so when all those lipoproteins are traveling around in the blood, normally they should just stream through, and maybe they'll bounce against the intima, but this is actually when they penetrate and get underneath the intima and they kind of burrow in to the muscular layer is when you start to form that atherosclerotic plaque that is so problematic for us. So it is this LDL particle that is the real problem. And even more so, we're starting to find out it's this ApoB lipoprotein that's part of that particle that we see helps cause this atherosclerotic plaque. Other lipoproteins can also contain ApoB, chylomicrons, some remnant lipoproteins such as VLDL or even some IDL, but mostly the 90 to 95% of all the particles that have ApoB will be LDL particles. So this LDL particle gets into the subendothelial space and it takes up residence into the muscular layer. And here it becomes subjected to oxidative forces, and all this bad stuff starts happening. And whenever bad stuff starts happening, we have inflammation that tries to eradicate it. Correct? You're all familiar with that. So we get full-blown inflammation, and all of our monocytes come in, and macrophages and mast cells. And mostly we talk about these macrophages becoming foam cells. They're called foam cells when they take up and try to digest all this fatty lipoprotein material. And at first, they're kind of successful in doing that. But eventually, it kind of overwhelms the macrophages, and there's more LDL particles than they can chew up. Like many immune processes, it becomes chronic and maladaptive, and then we start forming our atherosclerotic plaque. So then we have so many sterol-laden macrophages or foam cells, and they start to coalesce, and they recruit smooth muscle cells, and then you get some microvascularization, and eventually you get like a fibrous cap, and suddenly you have a big old inflamed plaque. And the plaque grows, and the plaque can grow out into the lumen and start narrowing the lumen, or it can rupture into the lumen and become a thrombosis. Eventually, even some of our T cells can come in, and that can lead to further destruction of the artery wall. And eventually, the lumen of the artery narrows, and fibrous caps develop and plaques take form. And most often, these are the plaques that will lead to a myocardial infarction or a heart attack when they dislodge and obstruct the blood flow in a coronary artery. Of course, they can obstruct the blood flow in a carotid artery or cerebral artery, and you have a stroke. Okay? So basically, if you want to stop atherosclerosis, our goal is that you must lower the LDL particle number. Okay? The low density lipoprotein particle number. And it is a numbers game. It's like how many LDL particles, molecules are shooting at, and if you just have so many of them in such a high concentration in your blood, there is no way that you can escape this happening. Okay, so here is a graph from your textbook, and it's cholesterol and heart disease, and it shows 10-year coronary artery death rate as compared to total serum cholesterol. And the only reason I'm really showing you this slide is to remind myself to tell you that total serum cholesterol is almost a useless number. You really have to go and do what we call a cholesterol fractionation and see what the specific particles that you're looking at. Okay? So cholesterol, is it truly evil? Remember on the first slide, it was one of my questions. And the answer is no. Cholesterol is part of every membrane of every cell in your body. Without cholesterol, there is no life. Cholesterol basically exists in two forms, either unesterified or free cholesterol and esterified cholesterol. And the form determines if we can absorb it or not, or store it or not. So much of the cholesterol that we eat is in the esterified form, and that is not absorbed, so it is excreted by our gut. It leaves our body through our stool. And the reason this occurs is that the esterified cholesterol not only has to be de-esterified, but it also competes for absorption with the vastly larger amounts of unesterified cholesterol that is supplied to us by the biliary route, which we just learned about, right? So, reabsorption of the cholesterol that we synthesize in our own body, our endogenously produced cholesterol, is the primary source of the cholesterol in our body. Most of the cholesterol in our body is made by our body. Let me repeat that. Most of the cholesterol in our body is made by our body, and that is why our anti-cholesterol drugs are so effective. It's not because they affect the cholesterol that we eat. So the process of regulating the cholesterol in our body is very complex, and there's multiple layers of control, and we just don't have time to go into it. But I do want you to know that without cholesterol, we're not going to have life. It's present in every cell of our body, that most of the cholesterol that we eat is not going to be absorbed by our bodies. So don't feel so bad eating your eggs. And most of the cholesterol that's in our body is the cholesterol that our body makes. Okay, so eating cholesterol has very little impact on the cholesterol levels in your body. And anyone who tells you otherwise just really doesn't know anything about it. And that's a lot of people. But I want you to know the real thing, okay? And I would say even lots of doctors out there really don't know this. And lipidology is a rapidly changing field, booming with information. So it's good that you know a little bit about it. So throughout your career here, you might be taught that you want your low to be low, meaning that you want your LDL to be low, and that is probably true. And you want your high to be high, or you want your high density lipoprotein, HDL, to be high. And that's a simple mnemonic device for remembering it, and you will probably get test questions correct remembering that. You might also be taught to think of these two things in terms of bad cholesterol being LDL and good cholesterol being HDL. But I want you to understand that this oversimplifies the whole cholesterol thing, okay? And it might be proven to be not quite correct, okay? So, as I said, this area of study is rapidly evolving. And if you want to explore lipidology further, a really good person to read is anything that you can find by Tom Dayspring. He's kind of like one of the big lipidologists in the country. And if you have cholesterol problems yourself, and maybe you can educate your own physician on this and do us all a service. Okay, so let's look also at lipid catabolism. So triglycerides that we learned are made from glycerol and fatty acids. When they're being catabolized, they are hydrolyzed to yield fatty acids and glycerol. The fate of glycerol is that it can be converted to glyceraldehyde 3-phosphate, or G3P, which is one of the intermediates in glycolysis. So once glycerol is converted to G3P, it can enter the glycolysis pathway that you are now so familiar with. Fatty acids are broken down by beta oxidation, and I was tempted to show you a slide of this, but I don't want to confuse you. Just know that they're broken down by a process called beta oxidation, which then transforms them into acetyl-CoA. And once again, they can enter the citric acid cycle. So the final process of lipid catabolism means that it can enter all the same reactions from there on out as carbohydrate metabolism. And I just wanted to show you another slide looking a little bit more up close at the components of a triglyceride molecule, which is the glycerol backbone and the 3 fatty acids attached to it. They condense to form the triglyceride molecule, and the triglyceride molecule can in turn be hydrolyzed into its component parts, which can go through the catabolic pathways that of glycolysis in the carboxylic acid cycle that you're already familiar with. And here's another slide that just kind of puts it into shorthand if you're better at remembering things in words. Triglycerides become fatty acids in glycerol. Glycerol gets broken down into G3P, which can enter glycolysis, and fatty acids first undergo beta oxidation to form acetyl-CoA, which can then enter the citric acid cycle. You should also know that we primarily use fats and carbohydrates as fuels. Carbohydrates preferentially our body uses first. And carbohydrates will yield 4.1 kilocalories of heat for every gram, whereas fats will yield 9 kilocalories of heat for every gram. So lipids are the preferred energy source for muscle, whereas glucose is the preferred energy for the brain or just about everywhere else. And when fats are being catabolized, and when they get catabolized at a rapid rate, you undergo ketogenesis because you're catabolizing these things so fast. What happens is that 2 units of acetyl-CoA will condense into the 4-carbon unit called acetoacetic acid, and that is a ketone body. And ketone bodies give off an acetone smell. People who are in ketosis, their breath smells a little bit like nail polish remover, acetone, okay? And here is a slide for fat mobilization and catabolism. This slide emphasizes the chief role of the liver for ketogenesis. Liver cells oxidize a small portion of ketone bodies for their own energy needs, but most of them are transported to the blood for other tissue cells for the change back to acetyl-CoA and oxidation via the citric acid cycle. So let's look at lipid anabolism. Lipid anabolism is also called lipogenesis, and it consists of the synthesis of various types of lipids, notably triglycerides, cholesterol, phospholipids, and prostaglandins, which get their name from the prostate gland. Triglycerides and structural lipids are synthesized from fatty acids and glycerol to form excess glucose or amino acids. The triglycerides are stored mainly in adipose tissue cells. These fat deposits will constitute the body's largest reserve energy source. This is in contrast to the carbohydrates, where only a few hundred grams can be stored as glycogen in the liver. Most fatty acids can be synthesized by the body, but some of them cannot, and these are called essential fatty acids. Omega-3 fatty acids are found in large quantities in fish oil and some plant oils like flaxseed oil. Some of the essential fatty acids serve as a source within the body for synthesis of an important group of lipids called prostaglandins. These are hormone-like compounds, and they're usually in the cell membranes. And from these prostaglandins, we have a lot of our inflammatory mediators. There are two major classes of polyunsaturated fatty acids, or PUFAs, and these are the omega-3 and omega-6 fatty acids. Most of us don't have any trouble getting the omega-6 fatty acids in our diet. And so a lot of fuss is made about the omega-3 fatty acids, in particular ALA, EPA, and DHA, which you see right here. Okay, so what are omega-3 fatty acids? As you see here, comparing the omega-3 to the omega-6, the omega-3s have a double bond at the third carbon atom from the end of the carbon change, whereas the omega-6s have it at the sixth carbon from the end of the carbon change. So let's talk about what all the fuss about the omega-3 fatty acids are. Omega-3s are present in certain foods such as flaxseed oil and fish, as well as dietary supplements such as fish oil. In fact, ALA is present in plant oils such as flaxseed, soybean, and canola oils, whereas DHA and EPA are present in fish oils, krill oil, but they're originally synthesized by microalgae, not by the fish themselves. So when the fish consume plankton, they accumulate the omega-3s in their tissues, and that's why you find omega-3s being really high in especially deep sea fish like mackerel or salmon. After we ingest the omega-3 fatty acids, just like all dietary lipids, they're hydrolyzed in the intestinal lumen, and their hydrolysis products, the monoglycerides and free fatty acids, are then incorporated into biosalt containing my cells and absorbed into the enterocytes by passive diffusion. Within the intestinal cells, free fatty acids are primarily incorporated into chylomicrons, and then they enter the circulation via the lymphatic system. The chylomicrons are in the chyle, right? Once in the bloodstream, these lipoprotein particles will circulate within the body and deliver lipids to various organs for subsequent oxidation, metabolism, and storage in the adipose tissues. Omega-3s play important roles in our body as components of the phospholipids that form the structure of cell membranes. DHA, in particular, is high in the retina, brain, and sperm. In addition to their structural role in cell membranes, omega-3s, along with omega-6s, provide energy for the body and are used to form eicosanoids, which are part of those prostaglandins, right? Eicosanoids are signaling molecules that have similar chemical structures to the fatty acids from which they are derived. They have wide-ranging functions in the body's cardiovascular, pulmonary, immune, and endocrine systems. The EPA and DHA will compete with arachidonic acid for synthesis of eicosanoids. So higher concentrations of EPA and DHA than arachidonic acid will tip the formation of the eicosanoid balance toward less inflammatory activity. So this is very good for wanting to reduce inflammation. And this is where we think that it helps with heart disease. Okay? So greater than 1 gram daily for at least a year has been shown to be protective against cardiac death, sudden death, and myocardial infarction, because they're supposed to be anti-inflammatory if you take fish oil. Okay, so this has been shown in several studies to reduce the risk of stroke and may even lower blood pressure. It might even help reduce the total blood triglyceride count. All right, so consumption of omega-3 fatty acids from marine sources lowers the markers of inflammation because the EPA and DHA will compete with arachidonic acid for synthesis of eicosanoids. These are all in the cell membrane, and they come out of the cell membrane during inflammatory processes. All right, there's probably more than you wanted to know, but we needed to talk about it just a little bit because there is a lot of fuss about fish oil. All right, lipid anabolism. And you could take fish oil tablets, or you could do what I try to do, which is eat salmon once a week because it is so delicious. I digress. Lipid metabolism is controlled mainly by the following hormones: insulin, adrenocorticotropic hormone, ACTH, growth hormone, and glucocorticoids. Always think cortisol when you see that word. So we primarily use our carbohydrates for energy first, but when our carbohydrate catabolism decreases below our energy needs, then increased secretion of hormones like growth hormone or ACTH and glucocorticoids follows, and in turn they'll bring about an increase in fat catabolism. If the carbohydrates are meeting our energy needs, then we're not going to catabolize our fats. So this is why it is said that carbohydrates have a fat-sparing effect. Another important hormone for the control of lipid metabolism is leptin. Leptin is secreted by fat-storing cells, and it seems to regulate satiety and how fat is metabolized. Okay, so let's go on to proteins. First, let's look at our sources of protein. Protein's monomeric unit is our amino acids, and our body synthesizes amino acids from other compounds in the body, but we only are able to make about half of the amino acids that we need. And of course, the amino acids that must be supplied by the diet are called our essential amino acids. Most of the food sources for our proteins will be things like muscle meat, or we do get protein from plants, but our plant sources have to be combined to provide all the amino acids. So if you're a vegetarian, there's lots of planning involved into making sure that you obtain complete proteins, meaning that you're obtaining all the essential amino acids. So let's examine protein metabolism. You previously spent lots of time in Bio 155 and in Anatomy 1 going through protein synthesis. So we're not going to go through it too in depth, but we'll just kind of remind ourselves about the process. First, remember that your cells synthesize their own structural proteins, and some special cells, such as the liver or some of our glands, other cells too, will synthesize proteins for export. Recall the central dogma of molecular biology. We have the DNA, our inheritance molecule, in the nucleus of our cells. And our DNA will unzip and it will be read by messenger RNA, which a RNA copy is transcribed off of a template strand of DNA. The mRNA then moves out of the nucleus and it goes out to get translated on ribosomes in the cytosol, either ribosomes that are free in the cytosol or ribosomes that are attached to the studded rough endoplasmic reticulum. And here's the process of protein metabolism, protein synthesis. All right, so as I said, we make an RNA transcript from the DNA in our nucleus. Enzymes will synthesize a complementary strand of RNA from the DNA template strand, and the transcript is edited. Only the exons are expressed, the introns are spliced out. And I'm leaving out lots of steps and all the enzymes and all that you learned, but we're just summarizing here to remind ourselves. Our mRNA moves out to the ribosomes where the transcript is translated. And in translation, our mRNA uses 3 base pairs at a time, the codon, that matches a transfer RNA's anticodon, which will bring the appropriate amino acid. Our amino acids then kind of knit together, forming a polypeptide chain in which a peptide bond is formed by the carboxylic end of one amino acid to the amine group on the next amino acid. And then, of course, our polypeptide chain can have post-translational processing and get packaged in the Golgi apparatus and all that. All right? So continuing with protein metabolism, let's look also at protein catabolism. The first step in protein catabolism occurs in liver cells. This process is deamination, in which we split off an amino group from the protein molecule to form ammonia and 1-keto acid. We'll go on to later excrete most of the urea through our urine. And the keto acid molecule can be either oxidized and enter the citric acid cycle, or it can be converted to glucose in the process known as gluconeogenesis, or form fat, lipogenesis. Protein catabolism and anabolism are happening simultaneously in your body, and it's the rates of the two that differ, and so we can have a difference of protein balance. You're in protein balance when the rate of protein anabolism is balanced with the rate of protein catabolism, and likewise, when the amount of nitrogen taken in is the same as the amount of nitrogen going out, you then also have nitrogen balance. If you're consuming a protein deficient diet, protein catabolism will exceed protein anabolism, and you are no longer in protein balance. When protein catabolism exceeds protein anabolism, the amount of nitrogen in the urine exceeds the amount of nitrogen in the food that you ingested. A person is then said to be in a state of negative nitrogen balance, or a state of tissue wasting, because more of the tissue proteins are being catabolized than being replaced by protein synthesis. Protein-poor diet, starvation, and wasting illnesses will produce negative nitrogen balance. A positive nitrogen balance occurs when protein anabolism is occurring at a faster rate than protein catabolism. A state of positive nitrogen balance therefore characterizes any condition in which large amounts of tissue are being synthesized. This is what occurs during pregnancy or growth, for instance. Protein metabolism is controlled by hormones rather than the nervous system. Growth hormone and testosterone both have a stimulating effect on protein synthesis. They are therefore called anabolic hormones. Catabolic hormones that have the most consequence are glucocorticoids, such as cortisol. They speed up tissue protein mobilization, or the hydrolysis of cell proteins to amino acids, and their entry into the blood. ACTH, adrenocorticotropic hormone, functions indirectly as a catabolic hormone because it stimulates the release of glucocorticoids from the adrenal gland. And glucocorticoids, of course, are catabolic hormones. Thyroid hormone is an anabolic hormone when there's plenty of carbohydrates and fats available for energy production. However, when these energy foods are deficient, or under conditions when thyroid hormone is excessive, such as hyperthyroidism, this hormone then promotes protein mobilization and catabolism. Let's now look at vitamins. Vitamins are complex organic compounds that are needed in small amounts by the body for normal growth and metabolism. And you'll find that many of our vitamins work with enzymes or coenzymes and help them to function. Vitamin B5, for example, is a component of coenzyme A, which you know as part of acetyl-CoA that enters the tricarboxylic acid cycle. Vitamin E prevents free radicals and other electron-seeking molecules from damaging the electron-dense molecules in cell membranes and DNA molecules. Your textbook on pages 948 and 949 will list the major vitamins and the major minerals and various functions that they have in your body and some of the deficiencies. So you probably want to look through that. But let's start talking a little bit about water-soluble vitamins, because I know not all of you necessarily have the textbook. Okay, so the water-soluble vitamins. You need to take in your water-soluble vitamins in frequent small doses. They travel freely throughout the body, and excess amounts are usually excreted by the kidneys, so they don't tend to accumulate and become some sort of toxic vitamin level. Niacin, vitamin B6, folate, choline, and vitamin C do have some upper consumption limits, but I think it'd be kind of hard I haven't ever seen that kind of vitamin poisoning. Vitamin B6 at high levels over a long period of time has been shown to cause irreversible nerve damage. And people who are older than 50 and some vegetarians might need to use supplements to get enough B12. I can tell you that you definitely need B12 and folate and pyridoxine, vitamin B6 for red blood cell formation, and that is often a heavily tested knowledge-based question. So know that for your formation of your red blood cells along with iron. And here's another tip, is that you actually need vitamin C as a cofactor to help you take up iron from your gut. So if you're trying to take iron pills for an iron deficiency anemia, you need to take vitamin C with it. And sometimes physicians actually fail to do that prescription. So here is a chart that starts some of your water-soluble vitamins that you can look at, the sources from where you get it, and the different functions. Also remember that when we get over here, the next page has a water-soluble vitamin. Folic acid is very, very important for pregnant ladies to take. It is needed for making new DNA and new cells along with the red blood cells, and deficiency of folate will cause neural tube defects. And that's another highly tested question. Okay, our fat-soluble vitamins, these are stored in our body cells, and so we don't have to eat them daily. You can have too much of a good thing with your fat-soluble vitamins, and they can achieve levels that can become toxic. And this tends to be more of a problem that we'll see with vitamin A and vitamin D. We'll discuss hypervitaminosis with vitamin A later on. So let's look at our fat-soluble vitamins. Vitamin A, needed for healthy skin and vision. Vitamin D is so important for calcium homeostasis. Vitamin E, that we went through, is an antioxidant and will protect your cell walls and protect your DNA from damage by free radicals. Vitamin K, that you get from your leafy green vegetables, the all too trendy kale. And that is needed for proper blood clotting. And that will actually be the antidote that you give for people when they take too much warfarin or Coumadin. Okay. Now let's look at minerals. Minerals are just as important as vitamins, and just like vitamins, we can have major amounts. We can have macrominerals and microminerals. One's needed in larger amounts and one's needed in smaller amounts. Minerals are organic elements or salts that are found naturally in the earth. Just like the vitamins, they can attach to enzymes or other organic molecules to help them work. Minerals like sodium and chloride and also potassium are really important electrolytes for maintaining our fluid and ion compositions. We want sodium and chloride to be high outside of the cell and potassium to be high inside of our cells. And of course, that will change when we're creating action potentials or some different ion flow through our membranes. Let's look at some of the important minerals that we need to consume. Okay, so chloride we need for proper fluid balance, and also remember the chloride tide in our stomach for forming our hydrochloric acid. Potassium, again, we also need that for proper fluid balance and very important for our action potentials and muscle contractions. Calcium, we need for healthy bones and teeth, as well as helping our muscles contract when all that calcium comes out of the sarcoplasmic reticulum. Calcium is important in nerve functioning and in blood clotting and blood pressure regulation. Phosphorus is also important for healthy bones and teeth, and it's found in every cell in the body, right? Because we have our phosphates. Sodium is needed for our proper fluid balance and for nerve transmission and muscle contraction. You find it just about everywhere, right? Magnesium is found in bones for making protein and for muscle contractions and nerve transmissions and a healthy immune system. Sulfur is found in protein molecules. And let's look a little bit more at our trace minerals. Okay, iron. Iron is very, very important, and the amounts that you need will vary throughout your lifespan, especially in females. As soon as you begin menstruating, you're going to need to have more iron, and when you're pregnant, you need more iron. It forms part of the hemoglobin molecule that's found in all the red blood cells, and that, of course, is necessary for the oxygen transport. Zinc is a really important molecule. It's part of many of our enzymes, and it's needed for making protein and genetic material. I don't know if you ever covered in Bio 155 about zinc fingers and all that for DNA. Anyway, it also has a function in taste perception and wound healing. I've seen strange rashes from a zinc deficiency in a patient. They had like a strange rash. We had to elucidate what the cause of that was, that occurred on the buttocks, and I guess that's a common area for when the zinc deficiency appears. Also, iodine is very important and really highly tested. It's found in part of thyroid hormone. This is why we have iodized salt. People had goiters in the Midwest, where we are. There was iodine deficient soil, and so they iodized all the salt so that people would have normal thyroid function and not have goiters. And selenium is also an antioxidant. Copper is part of many enzymes, and it's needed for iron metabolism. Manganese is also part of enzymes. Fluoride, of course, all you dental hygiene folks should know about this. It's involved in the formation of your bones and teeth, helps prevent tooth decay. Chromium is an interesting trace mineral. It works closely with insulin to regulate blood sugar, and chromium is also a supplement that many psychiatrists will prescribe for states of vegetative depression. This is not the hexavalent chromium that causes cancer and was made famous by Aaron Brockovich. This is usually chromium picolinate or trivalent chromium that helps, again, with vegetative depression. Molybdenum is also a trace element that is a part of some enzymes. Let's take a look at calcium intake in women. This is a slide that comes from your... As you know, calcium is a nutrient that's most commonly associated with the formation of bone, and about 99% of our total body calcium is found as calcium hydroxyapatite in bone, and it's what gives bone and teeth their hardness. But as we just said, it does function in the circulatory system, extracellular fluid, in the muscle and other tissues, and is critical for mediating vascular contraction and vasodilation, etc., etc. When we get to the endocrine section, you'll learn that calcium metabolism is regulated in large part by the parathyroid hormone vitamin D endocrine system. Our slide shows the calcium intake should increase throughout childhood and remain at a steady high level through adulthood, and actually increase in late adulthood or in postmenopausal women to ward off osteoporosis and other problems. The same figure shows us that the actual intake of calcium in reality amongst females in the United States tends to fall off during adulthood. And this increases the risk for osteoporosis and other disorders associated. Here we see that both males and females require a large amount of iron during the growth spurt that occurs during our teenage years. And the iron requirement then remains high for women during the rest of adulthood. This is because of the regular monthly menses. Iron requirements in women drop to the level similar to those of men after menopause. And both iron and calcium requirements, I should have pointed this out with calcium, grow during pregnancies. It didn't show the pregnancies on the calcium slide, but you do have increased calcium requirements during pregnancy, and you have sharply increased iron requirements during a pregnancy. This is because you're going to have the metabolic rate refers to the amount of energy that's released by the body in a given time through catabolism. It's the energy that must be expended in order to accomplish various kinds of work. In short, your metabolic rate is your catabolic rate, or the rate of the release of energy. Metabolic rates are expressed in one of two ways. First, it could be expressed in terms of the number of kilocalories of heat energy expended per hour or per day, or it can be expressed as a normal or definite percentage above or below normal. This is different from your basal metabolic rate. Your basal metabolic rate is the body's rate of expenditure of energy under basal conditions. So what then are basal conditions? This is when you are awake but resting. This means lying down, and as far as possible, you aren't moving a single muscle. You should be in the post-absorptive state 12 to 18 hours after the last meal, so you're not using your energy to digest. And you're in a comfortably warm environment, or the thermoneutral zone, which is a temperature range in which the metabolism is independent of ambient temperature. If you were cold, you would twitch your muscles in order to raise your body temperature, and that would raise your basal metabolic rate. The BMR is not the same thing as the minimum metabolic rate. It's not the smallest amount of energy that must be expended in order to sustain life. There are several factors that influence the basal metabolic rate. These include size, body composition, gender, age, thyroid hormone level, drugs that you might take, and several other factors. So let's examine some of these factors that determine the basal and total metabolic rates. A large individual would have the same BMR as a small person per square meter of body surface. Those with more lean tissue have more working tissue that uses energy at a faster rate than does storage tissue or fat tissue. Men have higher BMRs, about 5 to 7% higher for a given size and age than a female. In general, the younger an individual is, the higher their BMR will be for a given size and gender. Thyroid hormone, both the more active T3 and the lesser active T4, will stimulate your basal metabolism. Without a normal amount of this hormone in the blood, a normal BMR cannot be maintained. So those who are hypothyroid will have a lower BMR, and those who are hyperthyroid will have a high BMR. They will be catabolizing much faster. Body temperature also affects BMR. Fever will increase a BMR. For every degree Celsius increase in body temperature, metabolism increases about 13%. Hypothermia has the opposite effect. Certain drugs will affect metabolism, and you know this. All of you who come in with your coffee cup to every lecture, caffeine stimulates your BMR, focuses your attention. Amphetamines will increase your BMR. And of course, exogenous thyroid hormone would increase your BMR. And then there are other factors that will also increase your BMR. Things like emotions, pregnancy, and lactation. Lots of different things can contribute to increasing or decreasing your BMR. Okay, so let's look at the daily expenditure of energy. The left bar shows the total energy expenditure of the body as a combination of the basal metabolic rate, the thermic effect of food, everyday tasks, and purposeful exercise. The right bar shows the organs of the body that contribute to the basal metabolic rate. So it's no surprise that your resting muscles contribute, a very large amount, 18%. But your brain, especially as you're thinking through all this hard stuff, is probably way more than the 19% that it's showing on here. And your liver is going to be contributing a large percent because think of all the functions and synthetic functions that the liver contributes to in your body. And here's a slide that shows your body composition, the different body compositions for the male and the female, and basically how gender relates to BMR, with men oxidizing food approximately 5 to 7% faster than women. It's thought that this gender difference in BMR probably results from the difference in the proportion of body fat and muscle tissue, which is determined by our sex hormones. Women tend to have a higher percentage of body fat and thus lower lean mass than men do. So women are less metabolically active than men on the whole. And here's the basal metabolic rate and how it changes over the lifespan. Sadly, life is one slow decline of energy, and it looks like I'm down here almost on a plateau. Thankfully for you guys, you're still just on a really sharp downward trend, aren't you? You're just starting to get toward the plateau. Okay, now let's look at total metabolic rate. The total metabolic rate is the amount of energy used or expended by the body over a given time. It's expressed in kilocalories per hour or per day. So we have three important factors that seem to determine the total metabolic rate. Factor 1 is the BMR. So that's the energy used to do the work of maintaining life under the basal conditions that we just talked about. Factor 2 is the energy used to do all kinds of skeletal muscle work. This encompasses the simple activities like feeding yourself, getting your dupa out of bed every morning. And with coronavirus, we're probably doing a little other physical expenditure of energy other than that. And then factor 3 is the thermic effect of food. The metabolic rate increases for several hours after a meal, apparently because we need to expend energy to metabolize our food. And it takes a lot more energy to extract the energy from protein than it does from carbohydrates and fat. The energy balance and body weight. And this is kind of another controversial slide. So according to your textbook and sort of conventional wisdom, to maintain a stable body weight is basically the total calories in food ingested, or your energy input, should equal the total metabolic rate. This is basically the calories in, calories out theory. And it is falling out of favor increasingly. So with the calories in, calories out theory, basically, as the example in your book says, if you have a total metabolic rate of 2,000 calories per day and you consume 2,000 calories per day, then you'll maintain your body weight. However, your body weight will increase when your energy input exceeds your energy output. And conversely, your body weight will decrease when your energy input is less than your energy output. And I hope to show you in a minute why this is a little bit inane. First of all, it assumes that all calories are the same and that carbohydrates, fats, and proteins, the mix of what you eat doesn't seem to matter. And I would contend that it actually does. But probably for the time that you are answering test questions and board questions, you're likely going to have to answer them according to calories in and calories out theory. And get used to this in medicine. A lot of things that you think are out of mode and no longer the way that we truly think about issues are not always the way they're going to appear on board examinations. So think about this. Obese people tend to be at a stable weight for long periods of their life, just like lean people. So when their weight's stable, the obese and overweight are obviously in energy balance. They're not overeating during these periods of stable weight. They're eating to match their expenditure, doing exactly what lean people do. And the lean people get all the credit, right? The obvious question becomes, why are overweight and obese people only in energy balance when they're carrying around an extra 25, 30 pounds, right? When they have all this extra fat? And why are lean people in energy balance without all this excess? What is the dang culprit for that? Solve that. Why don't you? So let's say you're carrying around, 25 extra pounds. And you put on that 25 extra pounds over the course of 10, 20 years, as many of us do. So when you're nice and skinny in your 20s and you're still lovely and lean, and you then go on to celebrate, say your 40th birthday, and holy smokes, you gained, 25 pounds or so. And so your doctor or your nurse or, your nurse practitioner or PA is going to get on your case and extra you to eat less and get your dupa over into the gym regularly, right? So if you gain 40 pounds of fat over 20 years, that's an average of 2 pounds of excess fat accumulation every year. And since a pound of fat is roughly equal to 3,500 calories, this means you accumulate roughly 7,000 calories worth of fat every year. Divide that 7,000 calories by 365, and you get the number of calories of fat that you stored each day and never burned is the equivalent of 19 calories per day. And I'd really like you to convince me that 19 calories per day is what truly makes you fat over time. Do you really think that? Do you really think the calories in, a cheeseburger are the same as the calories in a salad? Is it just calories, or does the composition of what you eat actually matter? Now, if I ate 20 calories less every day, would I eventually evaporate? This whole thing just doesn't make sense, does it? So, I don't know. You arrive at your own conclusion, okay? Let's discuss starvation. Starvation is actually very interesting. So, food is primarily stored in the form of glycogen and fats. And your glycogen will get used up over 1 to 2 days. In starvation, we're going to burn our carbohydrates first, and then our fats. And finally, we start burning up our body, which is our proteins, our structural proteins. The only exception here is the skeletal muscle burns fat first. Okay, so the effects of starvation on the body. You have a nice slide that comes with your book that you can look at here. But I'd rather just talk about starvation. And the most interesting things to me were when I learned about the Minnesota starvation experiment. Because how do we know about starvation, right? So there actually was a clinical study conducted at the University of Minnesota during World War II. And they took the conscientious objectors, the people who refused to fight, and they decided to put them in Ansel Keys' lab over at University of Minnesota, where they volunteered, and let's put that in italics and quotes, that they volunteered themselves to be subject to a year-long nutritional deprivation study in which the United States government starved Mennonites, Quakers, all these peaceniks. So these 36 conscientious objectors participated in this study, and this is how we learned a lot about the effects of starvation. It's crazy, isn't it? Would never get past human human research subjects today, and thank God it would not. We also know a lot about starvation from examining members of the Irish Republican Army that went on a hunger strike. Probably the most famous of these is Bobby Sands. You'll find his face on the Irish postage stamp. And we basically found that you can last only a few days without water, but you can last, I think the average was 69 days without food. Bobby Sands died after 66 days. So cell survival depends on the proper operation of our metabolic pathways. Carbohydrates, proteins, and fats must all be available. We need specific vitamins and minerals for cellular metabolism, and they act a lot to work with our coenzymes and enzymes. Our nervous, skeletal, and muscular systems make it possible to take in complex foods, and our circulatory system transports the nutrients to cells. And so, as I said earlier, our circulatory system, our plasma is basically an aqueous solution, and so our fats, which are hydrophobic, need to be wrapped around in something that makes them a little bit more hydrophilic in order to get them to be transported. And that is our apolipoproteins to make our fats into lipoproteins. Our endocrine system, which we'll study later on, regulates the balance between the immediate use and storage. So we looked at eating disorders last time. Let's look at some vitamin disorders. So a vitamin deficiency is called an avitaminosis. And the classic vitamin deficiency is the lack of vitamin C, which is scurvy. Scurvy plagued the Pilgrims, Puritans, and early New World explorers. This is how the English sailors became known as limeys, is because they would suck on limes to prevent scurvy while on their transatlantic sailings. Vitamin C is a cofactor for the enzymes building collagen, and collagen is an important component in our connective tissues. And connective tissues connect everything. And so if suddenly you have connective tissue that is defective, you are no longer well connected. So the signs and symptoms, which might not occur until a few months after your dietary intake of vitamin C drops too low, will be things like bruising, bleeding gums, your teeth might actually fall out, weakness, fatigue, and a rash. You can also have a hypervitaminosis, and this doesn't tend to happen with our water-soluble vitamins. It happens with our fat-soluble vitamins that can build up in our cells. And a classic hypervitaminosis is hypervitaminosis A. Okay, so you can have hypervitaminosis A both in oral form and in topical form. So I don't know if any of you had acne as teens, but one of the drugs that they prescribe is a vitamin A derivative, and it is Accutane. Okay, so it builds up like a vitamin A in your systems, same sort of toxicity. You can have acute toxicities of vitamin A when you've ingested a large amount over a short period of time. And in these cases, you typically get dry lips, cheilitis, another type of dry lip, dry oral and ophthalmic and nasal mucosa. You can have a chronic toxicity, which is usually taking a more moderate intake over a longer duration. And here you tend to have problems with the resorption of bone, or you even inhibit the formation of bone. It leads to osteoporosis and hip fractures. You can get headaches, nausea, vomiting, whole bunch of other stuff. And in either case, either acute toxicity or chronic toxicity, the most severe and worrisome effect is teratogenicity. This is where you disturb the development of an embryo or a fetus. And this is why Accutane is contraindicated in reproductively active young women. So typically, Doctors will only prescribe Accutane in young women if they are also on a very good oral contraceptive. Some of them even make sure that it's a depot contraceptive. The topical retinoids, like Retin A, will tend to cause skin irritation. So you get redness and peeling. But also, they tell you not to use topical Retin A when you're pregnant because that too can prove to be teratogenic. Okay, so here let's look at our summary of metabolism. This is in your textbook. And we've gone through that whole carbohydrate metabolic pathway where you start out with glucose, you phosphorylate it, once it's taken up in the cells, it then goes into glycolysis. The pyruvate is formed. The pyruvate gets decarboxylated, and the remaining acetyl group joins up with coenzyme A, and that enters the tricarboxylic acid cycle or citric acid cycle. We create some coenzymes, we split off some more carbon groups, and then we enter the electron transport chain with all of those reduced coenzymes and form just a bunch of ATP, somewhere theoretically 36 ATP. Now you can see after we've done our lipid pathway that when we hydrolyze our lipids, we come out and have fatty acids and glycerol. The glycerol can join up as an intermediate in glycolysis as G3P and therefore goes on to the rest of the pyruvate acetyl-CoA tricarboxylic acid cycle and electron transport chain. And the fatty acid portion joins up with all that at the acetyl-CoA stage. In our protein pathway, our proteins can be hydrolyzed into component amino acids. Those amino acids will be deaminated, and the keto acid that is left over after the deamination will join. Some will join in and at the pyruvate stage, some will join in at the acetyl-CoA, and others will join in as keto acids in the tricarboxylic acid cycle. The ammonia left from the deamination will then be excreted in the urine. Let's go on to some practice questions. Protein or nitrogen balance means which of the following? That protein anabolism is equal to protein catabolism, that protein anabolism is greater than protein catabolism, or that protein anabolism is less than protein catabolism. And the answer, of course, is that protein anabolism is equal to protein catabolism when you are in nitrogen balance. What is the most common lipid in the diet? The phospholipids, cholesterol, triglycerides, or prostaglandins? And the answer, of course, is the triglycerides. Phospholipids are also common in the diet because they are the component of every cell membrane. What type of molecule is being shown in the accompanying figure? Is it a saturated fatty acid, an unsaturated fatty acid, a triglyceride, a wax, or a steroid? And you should know this, it's readily identifiable. The answer is it's an unsaturated fatty acid due to the double bonds. In a saturated fatty acid, every carbon is singly bonded to hydrogens or singly bonded to other carbons. The carbons are saturated with hydrogens. A triglyceride would contain a glycerol adjoined to 3 different fatty acid molecules. And a steroid, has that nucleus that's similar, that is the cholesterol nucleus, ring structures. The catabolism of fatty acids without any other food product availability causes the production of which of the following? Ammonia, glucose, ketone bodies, cholesterol, or ADP? And I think you know this. The answer is ketone bodies. The body first utilizes carbohydrates, then it will catabolize fatty acids, which will lead to ketone bodies, and lastly, it will burn protein as fuel. Anabolic hormones that stimulate human muscle growth by primarily increasing protein synthesis include all of the following except growth hormone, insulin-like growth factors, testosterone, and thyroid hormone. The answer is thyroid hormone. Thyroid hormone can be an anabolic hormone stimulating muscle growth, but it can also be a catabolic hormone. Say, for instance, under the condition of hyperthyroidism. Which of the following minerals is important in blood cell production? Magnesium, iron, manganese, iodine, and chromium. The answer, of course, is iron. Lipids are transported in blood as chylomicrons, lipoproteins, and fatty acids. Is this true or false? And of course, the answer is true. Lipids, which are nonpolar and hydrophobic, must be wrapped in a hydrophilic substance in order to be transported through the aqueous solution of the plasma or blood. Which of the following nutrients is important for erythrocyte production? Folate, iron, B12, pyridoxine, all of the above, or none of the above? And of course, we just did iron, so you know the answer could not be none of the above. And the answer is all of the above. Folate, iron, B12, and pyridoxine are all important in the manufacture of red blood cells. Which of the following vitamins is not stored in significant amounts in the body and must be continually supplied to the diet? The answer is the only water-soluble vitamin amongst the group, vitamin C. A diet that is low in carbohydrates would reduce the amount of fat in the body by causing fat to move out of the adipose tissue. And this, of course, is true. Rachel's total metabolic rate is 2,000 calories. Her basal metabolic rate is about 1,200 calories. Does this make sense? And yes, this is true. Your basal metabolic rate is always about 55 to 60% of your total metabolic rate, and 1,200 is 60% of 2,000. The conversion of proteins to glucose is an example of gluconeogenesis. True or false? It is true. Gluconeogenesis is making glucose from a source other than carbohydrates. High levels of apolipoprotein B, ApoB, and elevated LDL have been shown to cause atherosclerotic cardiovascular disease in adults. Is this a true statement or a false statement? And I do believe that you know, after my long explanation, that it is true. The sheer number of particles of ApoB and LDL have been shown to cause atherosclerosis. Remember, the ApoB and LDL burrows in under the intimal layer and into the medial layer or the muscular layer of the blood vessels. And then those foaming macrophages develop, leading to all the inflammation that starts the process of forming the plaque and atherosclerosis. The following hormones control lipid metabolism except insulin, growth hormone, adrenocorticotropic hormone, ACTH, cortisol, or epinephrine. And the answer here is epinephrine. I hope that you're happy to have finished this chapter. It was a long chapter full of physiology. I know I'm happy that it's over.